I'm Tom, and this is my presentation on atomic theory. Until the end of the 19th century, there was debate on the existence of atoms. It was a philosophical issue. What are we made of? I'm going to start by looking at the history of the atom. Atomic theory arose in ancient Greece, where it was led by Leucippus of Miletus and his disciple Democritus. The theory stated that each atom was homogeneous and indestructible, but different in size, arrangement, and shape. It theorized that all matter formed from a whirlwind of atoms in a void of space. Differences in atomic shape partially explain states of matter, but didn't address the role of temperature change. Atomic theory suggested that an omnipotent God could control a flurry of matter. Greece was a place of cutthroat competition between science and religion. The birth of atomic theory, however, was almost aided by religion. It seemed particles so small would never be observed individually. Proof would be hard to find. The technology had limitations. Atoms are so small that light is not affected when it passes through, so microscope technology is useless. To represent this, I tried to graph the wavelength of some visible light next to the radius of an atom. Scientists had to get creative. Joseph Thomson proposed a plum pudding model based on observations of separated charged particles. The model was tested in Rutherford's gold foil experiment of 1908. Alpha particles were shot at foil to observe the behavior of gold atoms. The experiment yielded 3 results. Most particles pass through, implying that atoms are mostly empty space. This disagrees with the plum pudding model. Some particles bounce straight back. This outcome appears remarkable. Rutherford is often quoted saying that it was like firing a bullet at a piece of tissue paper for it to come back and hit you. These results suggested that there was a dense nucleus within the atom. Some particles deflected, but only made slight deviations. This was a puzzling result. There was only obtuse deflections. Why was this a problem? An inelastic collision with a round object should be able to ricochet at close to a 90-degree angle with speed. The alpha particles were fired at random, and after millions of trials, this ricochet was never observed. Rutherford proposed that particles weren't ricocheting, but being repelled. Alpha particles are positively charged, so they can only be repelled by another positive charge. Under the plum pudding model, negative charges within the gold atom should balance the positive charges to neutral, and there shouldn't be repulsion. Rutherford concluded that there weren't negative charges in the nucleus. The nucleus is positive, with negatively charged electrons exterior. Thus, the positive nucleus could repel the alpha particles. Rutherford's developments were revolutionary, so I was upset to find this article. The gold foil experiment is traditionally simplified. The research happened over several months in different places by different people. The vagueness makes it difficult to find a clear aim or hypothesis, and there probably never was one. Scientists had no reason to believe that the plum pudding model was untrue, and so they had their own personal agendas before stumbling on this revelation. Hardly any ideas solely belonged to Rutherford. He connected the ideas of many. This key idea about the nature of science is wrongfully left out of history sections in physics textbooks. Rutherford's model didn't agree with contemporary physics. As electrons orbit, they are influenced by an electrostatic centripetal acceleration from the nucleus, which should cause radiation. But if electrons emit radiation, they'll lose energy and collapse into the nucleus. The imperfections of Rutherford's model were very clear, but there was no alternative. Niels Bohr generated postulates to resolve issues with Rutherford's atomic theory. Postulate 1. Electrons maintain a circular orbit around the nucleus under the electrostatic force given by Coulomb's law. Postulate 2. Only certain electron orbits are stable. In these orbits, electrons don't emit energy. The angular momentum of electrons in these orbits is quantized and given by nh over 2 pi. The value of n is an integer that denotes an electron orbits, and h is Planck's constant. Max Planck's work on quantization of energy enabled Bohr to apply quantum rules to atomic theory. Postulate 3. When electrons move to similar orbits, they emit radiation. It's like rolling downhill, but the energy leaves the electron nucleus system via self-perpetuating ripple of electromagnetism. Postulate 4. The radii of stable orbits is given by r equals nh over 2 pi mv. Bohr quantized angular momentum in postulate 2. Angular momentum can be represented with classical physics in terms of mass, velocity, and radius. If you equate Bohr's new equation with one from classical physics, you can see that radius is also quantized. The Bohr model built upon the traditional physics of electromagnetism and Planck's new quantum physics. Rutherford's alpha particles demonstrated atomic structure, but he didn't do it alone. Almost 100 years before the Bohr model was introduced, the spectroscope was invented, a tool which separates light into component wavelengths. When a continuous spectrum is shone through gas, some wavelengths don't emerge. Conversely, when the same gas is energized, it emits spectra of these same wavelengths. Bohr models could finally explain this phenomenon. Light is released when electrons move to a lower energy level. Classical theory of electromagnetism tells us that the energy of the electron nucleus system at certain levels is proportional to 1 over n squared. We can represent the energy of 2 different electron orbitals as k multiplied by 1 over n squared. Radiation energy can be represented as hc over lambda, so we can rearrange the wavelength. Johannes Rydberg already discovered this relationship empirically. This is the data that Rydberg would have had. Light intensity is being compared with the wavelength. The dips are where absorption has occurred. This is line spectrum. Rydberg may have wondered where the light goes after it passes through the gas. We know now that the absorbed light puts atoms in an excited state. These atoms will eventually emit the energy again and move to a low energy state due to the second law of thermodynamics. I'm going to analyze an atom of my second favorite element, phosphorus. I'm calculating the total energy of the electron nuclear system at each energy level. Finding kinetic energy requires algebraic manipulation. Phosphorus has an atomic number of 15, so I've subbed in a charge of negative 15e into Coulomb's law. Little q has been assigned a charge of 1e. Phosphorus can have multiple electrons, but we consider them individually. We can look at Coulomb's force in another way. Newton's laws show us that force is equal to mass multiplied by acceleration. This electron is in a constant circular orbit, so we can apply the formula for centripetal acceleration, which is v squared divided by radius. We can equate values for force. We want a magnitude on both sides, so I'm going to make the LHS positive. I cancel 1r, which gives me half mv squared on the left-hand side. Serendipitously, this is the equation for kinetic energy. The formula for potential energy is simple. The negative means that as the magnitude of potential energy increases, kinetic energy decreases. The law of conservation of energy still holds. Total energy is found. The only unknown remaining is orbital radius. If I found the radius of two different orbitals, I could find the change in energy as an electron jumps between them. I equated Coulomb and Newton's laws earlier to find kinetic energy. Now we're going to apply Bohr's quantum concept to the same equation to find quantized orbital radii. Bohr's fourth postulate gave us a relationship between velocity and radius with respect to energy level. I've used this equation to rearrange for v, then substitute this into our equation. It may look like a mess, but now I can solve for radius. Expanding and rearranging gives this relationship for r in terms of the principal quantum number. Besides n, these products are constant. They simplify to approximately 3.54 times 10 to the minus 12. If electrons are at their ground state, n will equal 1. This means that the smallest radius of a phosphorus atom is 3.54 times 10 to the minus 12, and the second smallest is 1.42 times 10 to the minus 11. I substituted these radii into my equation for energy levels and found the total energies of the nucleus electron system in the smallest and second smallest orbitals. These two energies were subtracted from each other to find the change in energy. Both terms represent the total energy of this system. Due to the law of conservation of energy, the change in energy should be zero unless there's been an external factor, such as the emission of an electromagnetic wave. The energy of a photon is hc over wavelength. I calculated a wavelength of about 5.43 angstrom. This isn't a wavelength on the real phosphorus spectra. It's an X-ray. My analysis of phosphorus is flawed. In nature, phosphorus inner two orbitals stay filled and the movement between them would be rare. Bohr's model was incomplete. Our modern understanding of the atom came from Louis de Broglie, Werner Heisenberg, and Erwin Schrödinger. In 1924, de Broglie published research suggesting that all matter has wave-like properties. His formula showed a relationship between wavelength and momentum. Electrons, considered like a wave, are still bound by the attractive force of the nucleus. They can be represented as a stationary wave. The distance from this wave to the nucleus remains the same as the radius predicted by Bohr. The wave-like properties of electron orbitals between Bohr's explain Bohr's second postulate. The reason why only certain orbits are stable is because destructive interference occurs on energy levels that have circumference not equal to an integer multiple of the wavelength, as you can see here. Schrödinger created a quantum equation to graph these waves. This equation represented probability densities of electron locations, and the electron cloud model was used to express this. The problem with waves is they don't have a position, but to consider momentum, we must consider masses as waves according to Broglie's wavelength. This forms the basis of Heisenberg's uncertainty principle. We need Schrödinger's cloud model because we can't map with certainty the behavior of electrons. Bohr's atomic theory is still applied by astronomers to determine elemental compositions of heavenly bodies. We can consider stars to be approximately blackbody radiators, which means they emit continuous spectra. As the light from stars passes through objects in space, photons are absorbed depending on the energy levels of the elements that compose these objects. We now know that each element has unique energy levels, so we can find what elements compose those objects based on the line spectra being absorbed. Some absorption will start occurring in the cool surface gases of the star. Not all absorption has occurred in the object of interest. Astronomers must observe the stars independently first to find a control. Although Bohr's model has evolved, his ideas can still be applied. His theory was an important step in the history of quantum physics. Thank you for listening.